please. Go ahead.
Hello, you can hear me? Okay. So, first of all, I'd like to thank you, the organizer, thank you, Hilda. It's on. Hello? Hello? Everything's fine? No. Okay. First of all, I'd like to thank you, Hilda. She convinced me to come. And also the organizers to put all the things together. And it's a pleasure to be here. I was here together with Marcos in one of the first seminars, and we followed how this grows. It's an amazing initiative. Congratulations for all. It's a privilege for our country to have an institute like that to hold like seminars, schools, postdocs, and wherever. And this is a very huge place, right? So, actually, I'm going to talk about São Paulo. No, it's similar because I'm going to talk about our brain. But São Paulo is like similar to our brain, right? You are in the largest town in the South America. We have a lot of connections, a lot of buildings interconnected. Sometimes a plane drop in your avenue and whatever. Well, and I'm going to talk a little bit about things related to synchronization. And it will be very easy because a lot of people have talked before, and some of them have already listened to my talk, so I apologize about that. But anyhow, just to talk a little bit, I'm from the Federal University of São Paulo, Universidade Federal de São Paulo. Actually, it started with a medical school, one of the oldest medical schools in São Paulo, and started in 1933. And later on, we started to change to university, and we have campus in this São Paulo area, Santos and São José dos Campos. The place where I live is located here. And we have a very interesting environment where people do a very interesting interdisciplinary work, including people with medical. And also this beautiful large house is this one where our medical school started. Escola Paulista de Medicina, Medicine São Paulo School. So, next time I invite you to visit us. But let us go back to track. So I'm going to talk about brain, neurons. This is the brain, this is the neuron. We have Professor Iberê here. He just, by the way, he just won a prize. Okay, a very nice prize. And this is Professor Iberê picture of his brain. And actually, you know, we have neurons. Neurons is like that. We have dendrites, axons, and they communicate it. And they, out of that, store informations and make us think, make us understand the world, and whatever. And what's very interesting about this, neuron is that you have like this behavior. This is a kind of oscillator. Then it goes like that. If you measure, we have some phases where is in this period that if you input something, he is not able to answer to the information, but it goes up and down, and we can measure. It is very interesting about that. Well, so, but what we wanted to do is to do a lot of simulations related to this issue. You know, we do a lot of things related to computational models. And this is amazing because out of experiments, we can build our model and draw a lot of information to make us understand better what is going on. And the main point is the synapse, this amazing connection between neurons that store information, that allow us to live and to understand the world somehow. And these neurons, they interconnect to each other, they change information through two ways, electrical synapse and chemical synapse, and one is faster than another, and here we are going to focus on this chemical synapses, is the focus of what we wanted. So, What is also amazing is that our brain, the neurons in our brain, they synchronize, you know? So, synchronization is the central point of the contemporary neuroscience, as we saw today. A lot of people before me talk about synchronization in the brain, and they will talk again later, okay? And actually, the synchronization, people believe that is the key phenomenon, the key process that allows us to think, to understand the world, to process information, and also to cognitive process and motor behavior. Actually, it's a very, very, very sophisticated structure with a lot of synchronizations around regions far away that interconnected to each other. So, but also if we synchronize a lot, we have some brain disorders like epilepsy, Parkinson's disease, autism, and we wanted to understand that and to avoid this thing or somehow to make these things happen. Synchronization is something that for some situations we want it, for other situations we don't want it. So, when we don't want synchronizations, today there is a very interesting way to treat that. It means deep brain stimulation. We saw this movement of this patient have seizure, and it's happened when we have some device, you know, that the implantation, this is in your skin, and here, you know, lead place, and it happens that it gives pulses, and out of these pulses, we can actually control the seizures. And it appears to be very efficient for Parkinson's disease, epilepsy, and also to treat potential tumors, dystonia, epilepsy, and obsessive-compulsive disorder, which is very important, right? You know, in Brazil, obsessive-compulsive disorder is a very important issue. People in Brazil eat a lot, you know, right? Go to the restaurants and things like that. But you know, it's very interesting, but the main point is that when you do that, the chirurgy, it's actually, you need to put the lead in your brain and try, go up and down until it works. And try an error, and sometimes it works, other times no, sometimes it started to work, but out of blue, it does not work anymore, and you need to get back to understand what's going on. But it is very promissory and very interesting to do that. Well, a friend of us, Vinicius Cotta, he tried to understand better this behavior, this phenomena. And he conducted a very important research using rats and this drug. And with this drug, he was able to make the rat get a seizure. And his goal is actually to put pulses, you can see, periodic one, actually 2 periods, random, and see the efficiency of this deep brain stimulation in rats. And it was experimental, it was very nice. If you visit him, you can saw the results. And he also were able to develop a new way to do that. But what is surprising is that he saw not only what he wants, of course, but also some non-standard form of low frequency, of low synchronization behavior on this research. And what happened, he saw that external perturbation can not only induce peak synchronization, but also reduce the abnormal synchronous pattern. So, out of this result, he started to understand, he does not have a lot of idea, and we decided to somehow do some play with that and build a model to help him to give some insights about his amazing work. So, let us talk a little bit, going back to this chemical communication between neurons. And actually, we know that the time delay on the brain signal propagation, it's very important because it happens when I have some input here. It takes some time until it goes all the way to the center of the nucleus of the neuron. So, in the axon, because of that, delays is a phenomena that took place, okay? And it's more important when we have chemical synapse. And in this case, when we have an input here until it goes there, we have a delay between 1 millisecond up to tens of milliseconds, okay? And in the dendrite, time delay is smaller than 1 millisecond. So, in order to understand the synchronization phenomena that we have in the brain, we need to take in consideration time delay. And also, maybe if you can have some control, some way to put some drugs that change this delay, we may be able to enhance or decrease the efficiency of the brain stimulation to do what we wanted to do in synchronization. So, here we are going to focus on that, chemical synapse and this time delay. So we're going to build a model where we have this kind of phenomena, this kind of synchronization, and to understand what's going on. So, so the time delay on the complex signal have important effects on the synchronization in the complex network. Here, we aim to explore the effects of delay, conductance on neuron synchronization activity. So, we wanted to understand how the time delay acts over a network of neurons during the synchronization activity, and how a network of neurons with delay react when pulsed inputs with different profiles are applied, not only the ones that the people use it. We consider, actually, to have insights about that, a random network of Hodgkin-Huxley neurons coupled by a way to simulate a chemical synapses. So, here we have our model, is a model for one neuron, very well known Hodgkin-Huxley models that do that. He capture actually the chemical connections, the chemical way that sodium, potassium goes through the membrane to the neuron. And actually of this model, we have a very, very, very interesting phenomena of the neuron that allow us to have a good model for the neuron activity that I showed you before. So here is, as it is, and how we model with a capacitance in that. And I draw your attention for these symbols, okay? Including the synapse current density that is very important to simulate the way the dynamics that the neuron works. So, actually, if you have this one neuron, this means that this external stimulus does not take in account. And what happens is that we have the following. Depending on this V, we can go to actually a fixed point, or it can oscillate it around, and in this case, we have actually a spike, okay? And actually, we have the ISE, the inter-spike interval, that we wanted to have in this interval. And actually, I0, we are going to use this interval following previous work that we have done on these issues. So, now we are going to pick up these neurons and integrate it in this complex network, random complex network, and we got this scenario, okay? And in this scenario, we have all this information here. We are going to use 100 Hodgkin-Huxley neurons coupled by excitatory chemical synapse. It means that we have delay. We have to build this network, a probability connection of 0.1, no auto connections. And actually, we also have these initial conditions. This is here is a random one. And actually, we have this term that represents the interaction between one neuron to the other, where we have the time delay here. And actually, we have the evolution of the synapse conductance from neuron K to neuron Y, because it decreases as time goes by. And Tk is the time that we have one spike. So this one, we are able to capture the connection in the network of the neuron as it goes through. And actually, I also wanted to draw your attention how each measure this time delay. You know, depending the time delay, what happens is the influence of one neuron to another will shift in time. So that if you are using like 13 milliseconds, you know, 0, it goes 1 in sharp, no time delay. As it's changed, it goes, keep going to the right, and so we add in this direction. It means that it does not intensify as in the case of 0. So according to the time delay that we are just using 1 for all the network, that will be changed, we have more or less intensive in the interaction between the neuron. So we have used all this value of parameters, whatever, and we are going to measure the system using those parameters, okay? Or those measure, I mean. So the phase measure, we use this way. This is a standard one, where we have a reference and a phase that allow us to know where we have the spike of one neuron related to another, and we can measure the phase. Kuramoto parameter, we can calculate it like that out of the phase that we we calculated previously. And 3 other measure that we're going to do is the mean synapse current density, that we are going to do the average in a time of the synaptic current density of the network, and the mean value of the current density interval, that the last interactions we are going to add and to calculate this average, and also the synapse current distribution that allows us to measure how is the shape of the distribution of the synaptic current density. So we have the Kuramoto parameter, and it goes on, they synchronize in phase, and we have actually this parameter, the mean of the current density, and we see, for example, in this case, where they synchronize, we have this value goes almost to 0, which means that they are deviated to this position, for example. So let us do the following. First, we are going to use 100 simulations on this model that I have shown you, and we have like that. This is the coupling between them, and we have this scenario. So when the coupling is very small in this position like that, look, we have almost a Gaussian, and so they add like that. It means that almost no variation, then no synchronization. But as we increases the gain, they go from this position to this position, where here you see how large is the excursion of the signal, and they synchronize. So no synchronization, synchronization according to the gain variation. Okay? So it's possible to see how the histogram of age, mean synaptic current density at time t for the last 5 seconds of the numerical simulation change as the system approached the synchronization, and we see this transformation when we do not have any time delay at all. Okay, so nothing happened at all. Now you can see what the scenario when we have time delay and no time delay. So for these 1, 2, 3 cases, with time delay less than actually 2 milliseconds, you can see that we almost have no variations in the Kuramoto parameter, in the parameter that we have, how the distribution of the curve is and actually, and how the mean current of the interaction is. But as the time delay increases, you see the difference up to a point that they do not synchronize anymore, right? It means that they goes to actually a Gaussian case in the current distribution, and actually you can see that what happened is this is increasing faster than it was before. And why this happened? Because with the time delay in general, this change of the influence of one neuron to to another, do like that. They actually hit the previous neuron in a position that they increases the level of the current in other time than the synchronization, and they don't synchronize, okay? So this is what happened because of the time delay. Well, so here what we did is to take a look of this phenomena in the state space, okay, in the parameter space, I mean. So you are able to see here the time delay, here's the gain of the network, and you are able to see how the synchronization phenomena, they develop as we change this bow parameter, and you see no delay, no time delay. It happens like that. As we increase the time delay, we go to a region that we do not have synchronization, and then the synchronization started to happen again. And actually, we can see the correspondence between this figure to this one, where we see this change, and we see very interesting phenomena pattern here. And here is also the average of the current density, and we see that this strange pattern also appear that has the consequences of decreases of increases the region of the synchronization. And here, actually, we did a difference between when we have no delay and we have the delay. And we see how this change as we increases in the parameter space. And you see, you can compare how significant is the relevance of the time delay for this phenomena of the synchronization, right? And you see this is a very important effect, and also this pattern that have a significant effect on this scenario. So our results suggest that values of tau, which are able to produce suppression of the synchronization activities, are in the range around 7 milliseconds, being more or less effective, depend of the gain. And why? Because the inter-spike time is 14 milliseconds. In 7, actually, we hit in the middle of them, so we increase the influence of one neuron to another, okay? As we have, as we have here, is the point that is suppress the activity. So, here we have the time delay. We just to draw the attention what's going on. And you see that even we use this time delay, for example, 0, 1 milliseconds, 2 milliseconds, 2 milliseconds in the border, and 14 milliseconds. And you can see that even when we have 0, they do not synchronize completely. They almost, sometimes they skip from the synchronization, but as we increase the delay, we have this effect. It is still, it keeps increasing, and then no synchronization, and then it go back because they interconnected. So now we are going to perturb this scenario, simulating that we have a brain stimulation. And we are going to do that, and we try to use two kind of perturbation: periodic pulse and random pulse. So here is on-off. You can see that, the cycle, and this is random pulse. And to actually to see if you're able to see the result, to have the results similar with Cotta did. And we see that for actually periodic pulses, it have and we have two scenarios: one with strong coupling, and other with not so strong couple, weak coupling. So with weak coupling, we have this scenario Actually, the periodic perturbed input, it can do a very, very, very strong effect that increases as the intensity of the perturbation, periodic perturbation, is larger. So we can see that using that, it increases the synchronization. And other way around, and appears other patterns that were not, they didn't appear previously. It means that when you use periodic signal, you do not only have the effect of take out the synchronization, but appears other very complicated synchronizations, scenario or not synchronization, or combination between synchronization and not synchronization, which means that we need to take care where to put the probe in order to take out or the synchronization or to put the synchronization back. It means that for weak coupling, that sometimes happen in all the parts, we need have to cautions in order to do that, and even small changes of the positions or of the spikes can completely change the results that we have it. And with all the way around, when we have a strongly coupling, we have the similar effect, but it's smaller than when we have weakly coupling. We see that the synchronization change, but it's more strongly, it's more effective. So when we have strong coupling, the effect of have periodic perturbed pulses is very, very, very effective. But even so, it appears some not expected phenomena like this one. And now, if we use random, we also have interesting results, but not effective as we have periodic one. So we use this distribution, and you see that it's changed the previous result without perturbation, but not that much. And also, it increases a little bit the regions where we have the synchronization, as you can see here. And this is the value of time delay in the middle of the interspikes, where the effect is larger one. So, our conclusion is the following. The time delays in the synaptic conductions can be effective to suppress spike synchronization in the random network of coupling Hodgkin-Huxley neural model. It means that time delay is very, very effective to do that, and we should maybe conceive a strategy to combine drugs that do a reduction or increase or control the time delay of the chemicals in the connection between the neurons together with the perturbation in order to have the result that we wanted. There is a relation between the perturbed interspike average interval and the time delay in which the effective of synchronization suppression is more effective. In the middle one, in the middle of the average value of interspike average. Both periodic and random pulse can reduce the interval of the time delay value in which the spike synchronization is suppressed. However, for time interval around the interspike average interval, the action of periodic pulse is able to generate synchronization even for small amplitude pulse. So, the main conclusion is that the combination of time delay, increase the time delay, and maybe periodic one is more effective in order to build with synchronization. So this is the people who work in this work, including Professor Caldas. He's there. And thank you so much for the time.
Thank you very nice. Thank you very much for the nice talk. Won't go too fast. There is some questions in the audience.
Yep.
Okay. Give me some time to get there. There's some delay. There's some delay in the communication.
Can you please go back to the slide? So it was the almost last, so where you have these synchronization structures with a periodic forcing. So where you had weak coupling and strong coupling in so to say, on both sides.
Hold on. Which one?
One more, I think. Yeah, here. Okay, so my question is the following. So when we compare the two kind of synchronization patterns, what we see, so then what is obvious on the left side is that you have, so to say, a kind of vertical structure popping
Right.
up, so which could be, because this is delta t, there is the period, if you like, of your forcing. Is this a kind of resonance structure, and why it's absent when you have a large coupling? So what is basically the mechanism of getting this type of vertical structure so that you have increased synchronization for the whole interval from the bottom, from tau equal to 0 to tau equal to 14?
Yes, good questions, Eureka. Actually, it started, actually this line, was not started exactly in the 0, but it's a kind of resonance effect, maybe, or the effect of the grid that we used. But it's a good question. Probably this is the effect of the grid that we are using, because we do not explore exactly the points located of that, because we expected that to have the same scenario of 0. Okay, but it's a good question.
Okay.
Yes, yes.
Yeah, look very different.
Right.
Any other question? No? Okay, then let's thank again the speaker.
Okay.
So now we move to the next speaker.